of my presentation today is molecular dynamic simulations of hyperphosphorylated tau protein with potential ligands from drug repurposing. The content of my presentation today includes research objectives. I will give an introduction of Alzheimer's disease, its pathophysiology, methodology, results and discussion and conclusion. The research objective includes to perform MD simulations of hyperphosphorylated tau protein with acinapine, paliperidone, and pentazocine to analyze the results of AMD simulations on hyperphosphorylated tau protein with ASE, PALI, and PAN to determine the bindings of ASE, PALI, and PAN to hyperphosphorylated tau protein. Alzheimer's disease is the most common cause of dementia worldwide, with global prevalence surpassing 150 million by 2050. It is a progressive chronic condition with cognitive dysfunction, mental symptoms, and behavioral abnormalities. Today, there is no effective drugs to cure or prevent Alzheimer's disease. This is an important point to know because it highlights that effective treatment for Alzheimer's disease remains an unmet medical need. Despite significant investment of resources and numerous research efforts in this area, this gap is what our research aims to address. Figure 1 shows the main pathophysiological mechanism involved in Alzheimer's disease. Alzheimer's disease drug discovery research studies focus mainly on reducing the amyloid plaque load in the brain. Because of its significant limitation and clinical failures related to our amyloid beta-based treatment, the involvement of hyperphosphorylated tau protein in neurofibrillary tangle production in Alzheimer's disease opened new doors for drug discovery. Figures 2 show the schematic diagram describing the healthy and Alzheimer's disease neuron according to tau hypothesis. Tau protein is important in stabilizing microtubules. The microtubules provide a framework for the transport of molecules within the neurons. So the tau protein is essential for preserving the structure and functionality of the neuron. Tau hypothesis proposes that the accumulation of abnormal tau protein in the brain is the major driver of Alzheimer's disease. This slide shows the methodology used for this research. We use AMBER for the MD simulation for 20 nanoseconds, which includes the minimization phase, heating phase, equilibration phase, reduction phase. Lastly, we perform the trajectory analysis. For results and discussion, we look into thermodynamic properties and structural properties. Overall stability of kinetic, total, and potential energies for AC, PALI, and PAN indicates the system were thermodynamically stable. All the systems were stable around 300 Kelvin. The pressure, volume, and density profiles for all three MD systems show a generally stable system in well-equilibrium state with consistent fluctuations throughout the entire simulation period. Root mean square deviation (RMSD) is a standard measure used in MD simulations to quantify the average displacement of a selection of atoms from a reference structure over time. Lower RMSD indicates structural stability, higher RMSD indicates significant conformational changes or instability. All the three ligands had higher RMSD values than the p-tau, indicating less stability and more conformational changes. ASE shows relatively stable interactions with p-tau. AST has an overall better stability in the entire system with RMSD around 7 to 10 Armstrong and a very stable binding site of low RMSD around 1 to 2 Armstrong. Root mean square fluctuation (RMSF) measures the atom deviations during MD simulation, showing protein flexibility and key residues contributing to molecular motions. RMSF analysis shows the differences in fluctuations compared to p-tau across various protein regions. ASE shows the overall lowest RMSF throughout the MD simulation trajectory. Radius of gyration (ROG) values reflect protein stability and flexibility, with lower values indicating greater stability. PAN seems to maintain a more compact and stable p-tau structure and it had the lowest ROG among the three systems. Hydrogen bond analysis is performed to understand the protein stability and evaluate the ligand binding. Looking at the table here, table 1 and table 2, the total number of hydrogen bond formed in AST with p-tau protein during the MD simulations was 46, with the highest occupancy was 20.8%. On the other hand, the total number of hydrogen bond forms in PALI involving the ligands was only 7, with the highest occupancy of 1.9% only. There is no hydrogen bond formation at all in the PAN system. In conclusion, it is evident that the structural bioinformatics methods were useful in evaluating the binding potential of repurposed drug candidates on hyperphosphorylated tau protein. ASC is the most promising drug candidate among the three investigated drugs to act as p-tau aggregation inhibitor based on the results from the MD simulation. Suggestions include conducting longer simulations to obtain more information, including the MMPBSA and in-depth experimental work. Thank you, and I welcome any questions.